Thanks. Thanks for giving me the opportunity to present my work here. So I'll be talking about 20 centimeter intensity mapping with upgraded GMRT, and this is third work of a series of work that we are doing with data from uGMRT. So for those who don't know, GMRT is a very big radio telescope in India. It is 80 kilometers away from Pune city. And this work I'm doing at IIT Kharagpur. I'm a PhD student there with Professor Somnath Bharadwaj and others. So earlier people have explained this. I'll be very brief. So after CMBR, we have this neutral region. Then we got this reionization, epoch of reionization. And my concern is on this post-reionization epoch. So in this epoch, the neutral hydrogen is in these galaxies. These are plotted in these dots. And the rest of the intergalactic medium is ionized. And all the neutral hydrogen that I'm concerned about are inside these galaxies. So this is also been explained. So I'll be considering I am trying to detect the redshifted 21 centimeter line from a redshift, which is around 2.3. I'll introduce the data later. So this 21 centimeter intensity mapping from the post-UR, we can do some specific things like that. It traces the neutral hydrogen, traces the matter distribution in this region. So it's a very good probe to the large scale structures. We can constrain the dark energy equation of states by measuring the baryon acoustic oscillation features in the power spectrum. Even with independent of power, even with the independent of BAO, we can also measure cosmological parameters. One can quantify non-Gaussianity if there is any, and constrain UR models like the late reionization and these kind of things. So what we do is that we look at a patch of the sky through a interferometer or single dish telescope and try to find something like this kind of thing, the brightness temperature fluctuation of the 21 centimeter signal. So our aim is to measure the integral emission of the 21 centimeter signal instead of individually detecting the galaxies, which are very distant and can be very faint. So this is the broad idea of 21 centimeter intensity mapping at the post-EOR. But when we try to measure these features, what we get actually is this kind of galaxies and diffused emission. These diffused emissions are basically synchronous emissions from our own galaxy and other galaxies. And these are continuum emissions, and we can find it at all frequency below 1420. So we cannot do any field level inference from here. So how to remove them? So our idea is to get some summary statistics. So what we do is quantify this quantity, my multi-frequency angular power spectrum. So the idea is to decompose the brightness temperature fluctuations in terms of spherical harmonics and cross-correlate. So once again, the 2-point correlation of these harmonics at different frequency to get this quantity multi-frequency angular power spectrum. And at this epoch, it is also a nice idea to assume ergodicity of the signal. So it depends only on the separation between the two frequencies. So we can rewrite it in terms of delta nu. So when we measure the measurements are done with GMRT, and when we measure, we see these high values. These measurements, these are all from real data, and these kind of oscillations. So this is done in 610 megahertz, 150 megahertz, similar features, and recently at 430 megahertz. So these are signatures of foregrounds. I don't want to go into the details of why these kind of structures comes up, but our idea is how to remove them. So for that, we need a prediction of the 21 centimeter signal, how the 21 centimeter signal behaves, what the multi-frequency angular power spectrum of the signal, how does it behave? And with this, we will try to remove those foregrounds. So the 21 centimeter signal can be, the predicted signal can be written in terms of the matter power spectrum, which is the Fourier transform of the power spectrum along this line of sight and this bias parameter. The idea is that the 21 centimeter signal, it is a line emission, so it decorrelates very fast when we correlate along the frequency. So you can see from this particular L that the high amplitude goes very fast to very low amplitude, and this dark black line is where the amplitude falls to 90% from its initial amplitude. So in this region, there is very little or no signal, and the signal is mainly in this 0.5 megahertz but the foregrounds are continuum emissions, so they remain correlated across this bandwidth. So if you see these measured data points, here the foregrounds are almost correlated. Initial amplitude is 0.16 millikelvin square, and it is almost half by this 4 megahertz bandwidth, whereas the 21 centimeters predicted 21 centimeter signal, this amplitude is 90%. It has fallen to 90%. So the idea is that we model these regions on the measured data and get our best fit models. So we model with a polynomial, an even polynomial, and then extrapolate those best fit models here so that we can get a best fit foreground model in this region. And the residuals from this region is what we expect to have the 21 centimeter signal and noise and possibly some systematics, which we don't know. And we have used this tapered grid estimator. It is not possible to go into the details of this, so I am showing them some references here. So this is the data. Data is not important here, but I have to show that we have used this 24 megahertz bandwidth data here. But this method can be applied to anywhere, to any frequencies, EOR and the post-EOR. So I'll skip this. So these are the results. So this is at a particular L value. This is the blue curve is the measured data, and the red one is the best fit. So we have used only this region, the region right side of this vertical dashed line, to get the best fit model and extrapolated it back there. So these are some of the L values. There are many other L values. I've shown these three. And these are the residuals, which comes only from this region. So these residuals, and these are the 2 sigma error bars due to noise, and they are consistent with 0. There are some issues which I shall discuss if I have time later. So we have these residuals. We have this measured CL delta nu. We reviewed the foreground models, and we use the same methods in the predicted 21 centimeter signal to account for any kind of signal loss due to this polynomial fitting. And this is our residual. So this is our model. The residual, we assume this to follow the 20 centimeter signal through this bias parameter, which we try to estimate, and we have this residual which we expect to be noise if we have removed the foregrounds properly. And this is when we use all these residual points, available points, we get an upper limit on the 20 centimeter on this parameter omega h and bh1. We have divided the data in 3 sets. For ease of this analysis, and we have separately estimated this omega h and bh1 at different length scales. So these are length scale. So this is a baseline range, so it is better to show in the length scale, but this is what I have right now. The best result we get from combining all these values, and is around 0.22. Which is around 10 times larger than the expected value at this redshift. So we still have a large range to cover. And if we do a Fourier transform of this CL delta nu, the maps, which is the 2-point correlation across frequency, then we get the power spectrum. And before the foreground removal, the power spectrum looks like this, where these red regions show the large foregrounds, because the foregrounds are smooth in this correlation function. So that's why it is there in this low K modes, and usually people avoid these K modes and estimates the 21 centimeter power spectrum in these modes, but then we lose a lot of information. But here we are able to remove those high value regions, and we are able to use the whole region. If you see the statistics of this region, we have estimated the statistics to this quantity, this power spectrum, by the error in the power spectrum, which we estimated from simulations. And you see that this is quite similar, symmetric from the 0 line. We have a slightly non-zero positive mean, which suggests that there might be some foregrounds there. And this sigma is expected to be 1 if we have a Gaussian noise, but this is slightly larger than 1. And we use these values, these power spectrum measurements, to finally calculate the spherical power spectrum, where we assume the spherical isotropic nature of the 20 centimeter signal. And we have compared these results. This red results is what we get from foreground removal. We compare it with the earlier results, which is shown in orange line, which uses foreground avoidance. And these are quite similar in this range, but with foreground removal, we are able to probe to larger scales. And these are some earlier results which we previously obtained from the same data and which uses a slightly different technique, but it is not possible to go into the detail of these things. I will refer you to our earlier papers for that. And this is our best results for different K values, and the tightest upper limit is around 20 millikelvin square. And one thing to notice is that we have reached the signal to noise. We have reached the noise level almost in all the K beans, apart from these 2 beans where it is slightly more than 2 sigma. It is better to be in the 2 sigma region. The people usually do that. This is a summary of the results what we get so far from the band 3 data. We're still trying to analyze deeper into this data, and this is the tentative results. We are still in the review process. The review was good. And some issues we faced, which I wanted to discuss, that the residuals we get, we see that they are not random properly, they're not totally random. There is some correlations. We don't know how to deal with that. But when we see the statistics, it is nearly symmetric, but at individual angular multiples, there are some correlations. And we presently don't know how to deal with that. So any comments would be helpful. And we should have plotted error bars in our best fit model, but we didn't do that when we submit our paper. So we are not trying to use different methods to predict error in these extrapolated regions. So we have tried with Gaussian process regression. And these are the error bars when you predict the best fit model with Gaussian process regression. But the problem with this is that only polynomial covariance function is found to work. If we use any other, so this is a predicted 21 centimeter signal for this particular L value, and we use GPR on this. We have modeled this region only and extrapolated in this region. And we see that if we use polynomial covariance function, we only lose very little amount of signal. But for other covariance function, which I have checked, they try to follow this small bump here and try to fit out this signal out. So other than the polynomial covariance function, no covariance function were found to work. So this is another issue. So I would like to summarize now. So this intensity mapping of the 20 centimeter signal is a promising cosmological probe. The primary hindrance are foregrounds. We have attempted to remove the foregrounds based on these 2 features. This 20 centimeter signal being a line emission, it decorrelates faster, whereas foregrounds, they are significantly correlated across the bandwidth. And after removing the foregrounds, we get this best upper limit is the 0.22, which is nearly 10 times larger than the expected value at this redshift. We don't know how to deal with the correlated residuals. Maybe they are systematics or something we don't know. And GPR, we found that GPR works in this method works, but only with polynomial covariance. So thank you, and any questions? Yes,